This video is about using truth trees to test for entailment and logical equivalence. Remember that an argument is valid if and only if the truth tree that begins with its premises and the negation of its conclusion closes. If the truth tree closes, then the argument is valid. Now, when an argument is valid, we also say that the premises entail the conclusion. And the way we write that down is we say that the set consisting of the premises entail the conclusion. So it's going to turn out that a set entails a sentence Q if and only if, when we stack the members of the set and the sentence that may or may not be entailed and negate it, the tree closes. Okay, so if we stack the members of the set and the negation of the sentence that may or may not be entailed, and we get that the tree closes, then this entailment holds. So we can use a truth tree test to test for an entailment. So let's think of a simple example to illustrate this point. We're going to test to see whether the set A arrow B entails, so we're not sure if it does, so let me write it as a question. Does the set entail the sentence neg A or B? And to test this, we're going to begin a truth tree by stacking the members of the set. There's only one member of the set, and the negation of the sentence that may or may not be entailed. You can finish out this truth tree yourself, and you will see that the tree closes. So what we can conclude is that the set A arrow B, that is to say the set that contains the sentence A arrow B, entails neg A or B. And we can also think of this as an argument. What we're saying is that A arrow B, therefore, neg A or B is valid. And this should not surprise us. And it shouldn't surprise us because we remember that A arrow B is logically equivalent to neg A or B. So if we remember that they're logically equivalent, then we know that there's never going to be a case where A arrow B is true and neg A or B is false, because since they're logically equivalent, that means that they always have the same truth values. So there will never be a time when the premise is true and the conclusion is false. That is to say, the argument is not invalid, so it's valid. And we can reason the other way as well. Once we know that the argument is valid, we can see that there's never going to be a time when the premise is true and the conclusion is false. And if we also checked the argument that has neg A or B as the premise and A arrow B as the conclusion, we would discover that that's valid as well. And that would lead us to conclude that they always have the same truth values, and so they're logically equivalent. So what we've done here is discover a key result in an example, and the key result we can write down as a general claim that we could prove. I'm not going to stop to prove it, but we could prove it. And the result is this. The result is that two sentences of LP, script P and script Q, are logically equivalent if and only if they entail each other. And let me be clear about what I mean by they entail each other. That is, if the set containing script P entails Q, and the set containing Q entails P. If both of those entailments hold, then the sentences are logically equivalent. And if the sentences are logically equivalent, then those two entailments hold. So this key result here is something that we can prove in general. We're not going to stop to do it, but we're going to use this key result to develop a procedure using truth trees for testing for logical equivalence. Because we're basically now going to say that we can use truth trees to check these two entailments down here, and if both of those truth trees close, then the two sentences will be logically equivalent. Let's write that out as a procedure with steps. And we're going to set it up as though we have a problem that we're trying to solve, and then we're going to solve the problem with a decision tree. So the problem is to determine whether P and Q are logically equivalent. And our solution is to use a decision tree that's going to look like this. First, we're going to ask, does the set containing P entail Q? Remember, we're going to answer that question with a truth tree by setting up a truth tree that begins with P stacked on top of neg Q. And we're going to have a yes or no answer from the truth tree. If the truth tree tells us that the set containing P does not entail Q, then what we know is that they're not logically equivalent. If the truth tree closes, which shows that the set P does entail Q, then what we know is that we need to ask another question. Now we need to know, does Q entail P? And again, the truth tree is going to give us a yes or no answer. If the truth tree says, no, Q does not entail P, then we know that they are not logically equivalent. And if the truth tree says that the set containing Q does entail P, then I know that they are logically equivalent. So using this approach, we can answer the question about whether or not two sentences are logically equivalent by constructing at most two truth trees to answer in the affirmative, yes, they are logically equivalent. Or if they are not logically equivalent, we might discover that after one truth tree. If we happen to get lucky, or we might have to do two truth trees and then discover that they're not logically equivalent. So let's do a couple of quick examples to show how we use this procedure. So in the first example, what we're trying to decide is the following. We're going to ask, is the sentence neg A arrow B logically equivalent to the sentence A and neg B? And so to answer this, we're going to check two entailments. So to be clear about that, let me just put it like this. Our first step is check to see whether the set containing neg of A arrow B entails A and neg B. If the answer is no, we're done because they can't be logically equivalent. If the answer is yes, we have to build another truth tree. So to check this, we proceed in the usual way. We start with stacking the members of the set. And here, this truth tree is very simple. So let's just do it quickly. So this is going to stack. So we're going to have A, neg B. Those came from 1. And then this is going to branch. And we're going to have neg A, neg B. That came from 2. The left branch closes. The right branch we have to decompose to B from 5, but then it closes. So what we've discovered is that the set containing neg A, arrow B, does in fact entail A and neg B. We're not done because this does not yet show that they're logically equivalent. It only shows that the first sentence here, which we could call P, entails Q. That's this one here. But it doesn't show that Q entails P. So that's something we have to check separately. So let's do that now. So now we're going to check, does the set containing A and neg B entail the negation of A arrow B? Let me just tidy that up just a little bit here, A and neg B. And again, we know how to do this. This is easy. We just stack the members of the set, and here we only have 1, A and neg B, with the negation of the sentence that may or may not be entailed. And in this case, we're going to write out the negations explicitly. So it's the negation of the sentence that is the negation of A arrow B. And yes, indeed, we can, as our very first step, get rid of that double negation. So we have this. And again, we have a very simple truth tree here. We have one sentence that stacks, the other one that branches. So let's do the stack first. We have A, neg B, like this. Both of those came from 1. And then it branches, and we get neg A, B, and both of these close on line 6 from line 3. And so what we've now discovered is that the set containing A and neg B entails the negation of A arrow B. So now that we have discovered that both sentences entail each other, now we can conclude that the two sentences are logically equivalent. So to be a little bit not completely rigorous here and save a little bit of time writing, we could write it like this. We could say that the negation of A arrow B both is entailed by and entails A and neg B. And so therefore, the negation of A arrow B is logically equivalent to A and neg B. And so by getting rid of the set notation up here, I make it really obvious that there's an entailment that goes in both directions, right? The sentence on the left entails the one on the right, and the one on the right entails the one on the left. And so the two sentences are logically equivalent. And that's all there is to this kind of work. And so I hope you'll be very successful at doing exercises.